Hello students, hope you are doing well. In this video we are going to look at some topics of rotational motion. In fact, here we'll be introducing all the new terms that we are going to learn in rotational motion. So we call it as rotational kinematics. So here, as I told you, we'll be looking into the new terms that will be using throughout the topic. Now in rotational kinematics, first let's define what is angular displacement. What do we understand by angular displacement? I can see the figure here. It shows a circular path. There is an arc length S, which is, the shaded region. If you can see that there is an arc length S, which is on the circumference, and angle theta. Now this theta is called angular displacement. So how do I define it? I can say angular displacement as the angle subtended or angle covered by a body. Right? So in this case, for a linear distance of S along the arc, angular displacement is theta. This is the angle that has been covered. Now what is the relation between theta and S? I can write S equal to R theta, right? S equal to R theta. Now this S equal to R theta is only valid when theta is in radians, otherwise it's not valid. Then we have angular velocity. Now what is linear velocity? Linear velocity is change in position by time, or it is rate of change in position. So here, as we have said, angular displacement is angle covered by the body or change in angular positions. So angular velocity would be rate of change in angular positions or rate of change in angular position. That's what is angular velocity. So how can I define it? We represent it by omega. So omega equal to how much? I can write it as d theta by dt. So from this, so if I want to have a relation between linear tangential velocity and omega, now omega can be written as, so if I use this expression theta can be written as S by R. So I can say theta d theta by dt equal to 1 by R into ds by dt. Now ds by dt will become tangential velocity, so I can write omega equal to v by R. So this is the relation between omega, that is angular velocity, and v, that is linear velocity, where R is the radius. Then angular acceleration, we define linear acceleration to be rate of change in velocity of the body. So angular acceleration is what? Rate of change in angular velocity. Rate of change in angular velocity. So this is represented by alpha. I can write alpha equal to d omega by dt. And if we are looking at average values, so I can say alpha average equal to final angular velocity minus initial angular velocity by time. This is average angular acceleration. So we have angular displacement. Angular displacement is change in angular position or angular power covered by a body. Angular velocity, rate of change in angular position, and angular acceleration, rate of change in angular velocities. So all these are rotational analogs of linear quantities. Then let's look at relation between linear and angular quantities. We just seen that. So what is it? One is I can write S equal to R theta, right? We have just seen that S equal to R theta. What is S? S is, I can say, displacement along the arc or distance covered along the arc. And R is radius, right? Similarly, we have seen that omega equal to V by R. So that can be written as V equal to R omega. Omega, we know it is angular velocity. What is V? V is tangential velocity. Similarly, alpha can be written as alpha, we know alpha is equal to how much? D omega by dt. We have seen that. So I can write A equal to R into alpha. where A is tangential acceleration. Right? So A equal to R alpha. Alpha is angular acceleration. So these are the relations that we use when we convert angular quantities into respective tangential quantities. Tangential quantities are linear quantities. Now let's look at equations of this rotational motion like equations of normal motion when acceleration is constant. In fact, angular acceleration is constant. So let's first of all write down the equations of linear motion. What are the equations that we have? We have V equal to U plus AT, S equal to UT plus half AT square, and V square minus U square equal to 2AS. Right? This is what we have. Now the equivalent angular equations are V is final velocity. So here it is final angular velocity equal to initial angular velocity plus alpha t. Now for this S equal to ut plus half at square, S is linear displacement. So angular displacement equal to U is initial linear velocity omega I into t, initial angular velocity into time, plus half A is acceleration, so angular acceleration alpha into t square. And coming to the third equation, v square minus u square equal to 2as, I can write omega final square minus omega initial square equal to 2 into alpha into theta. So these are the three equations relating angular quantities, that are angular velocity, angular acceleration, and angular displacement when angular acceleration is constant. So as stated above, these are only valid when alpha is constant. If alpha is not constant, we cannot use this. So depending on situation, what all variables are given, we can use any of these equations. And if at all you forget these things, you can just remember the equivalent linears one, and from there you can write down this angular equations also. Now let's look at equations when angular acceleration is changing. So again, when acceleration is changing, we have to go for differential equations. We'll use the basic equations. What we know angular velocity omega equal to d theta by dt, right? So from this I can write d theta equal to omega dt. So delta theta, that is change in angular position or angular displacement, equal to integral theta t1 to t2 omega dt, right? So this will give me change in angular position, and this will give me angular velocity when position is given as a function of time. Now similarly, what do we know? We have angular acceleration, the other equations, like we have v square minus u square equal to s and all those things. Now if I want to find angular acceleration, we know d omega by dt equal to alpha. From this what I can write? I can write delta omega equal to integral t1 to t2 alpha dt. So this will give me change in angular velocity. Similarly, so this is, yeah. Now we have the other equation when omega is given in terms of if theta is given in terms of x, or omega is given in terms of theta. In that case, what do we do? So we have alpha equal to how much? D omega by dt. I'll multiply and divide by d theta. So alpha can be written as d omega by d theta into d theta by dt. So alpha can be written as d theta by dt is omega into d omega by d theta. So this is when omega is given in terms of theta, we can find angular acceleration by using this expression. Similarly, if I want to find omega from this, what will I get? I'll get alpha d theta integral would be equal to how much? Integral omega d omega. From this I can have a relation between alpha and omega. Hope this is clear. So these are the equations which are always valid irrespective of whether angular acceleration is constant or not constant. But when angular acceleration is constant, we already seen that we use the equations that we have seen in the last slide. So this we restrict ourselves to a usage when the angular acceleration is changing. Hope you could follow this. So what all things we have done in this particular video, we have defined the angular quantities, that is angular displacement, angular velocity, and angular acceleration. Then we have written down the equations when angular acceleration is constant, and then we have written down equations when angular acceleration is changing. Hope you could follow this. Thank you very much.